Hi everyone, this is Dr. Sandeep, Associate Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss about the development of microstructure in the isomorphous alloys. So what is the development? Development means how the body is being cooling slowly or in the equilibrium condition or non-equilibrium condition. So we will discuss both these at equilibrium condition and non-equilibrium condition, how the metal is being cooling, so that during this cooling process, what is the changes in the microstructure, that is the development of the microstructure in the isomorphous alloys based upon the temperature and the equilibrium conditions. So what is an equilibrium condition means? So when a body is heated to its melting temperature, now the body is to be cooled. So during the process of cooling, what happens when the body is slowly getting cooling, then that type of system is called as equilibrium. That means at equal distributions, the heat is being lost during the cooling process. So slowly this process is being cooled. Now during this cooling process, what are the changes in the microstructure at different temperatures? We'll find out, and how to locate those microstructures and how to find out what is the composition between these cooling process we'll see. So now equilibrium cooling in the development of microstructure for the isomorphous alloys. So what happens? In the previous session we have discussed about the at a point we are calculating what is the composition, how we are trying to get the composition based upon the tie-line method. So because of the tie-line method, we are going to find out what is the composition and what is the temperature at that given point. Now, suppose if you consider the same example of the system, here we are having nickel and copper as an example to illustrate this equilibrium condition. Now we are considering a nickel and copper system, specifically of that alloy composition which is having 35% of nickel and 65% of copper. So at that point, that means this is the 35% of nickel and 65% of copper. So this has to be cooled from 1300 degrees centigrade. Why at 1300 degrees centigrade means that is the melting temperature of that point. So beyond that point, the melting starts. Before that, the solidification will start. So now from 1300 degrees centigrade, the system or that alloy has to be cooled. Now during this cooling process, there are a lot of changes in the microstructure. So when there is in the liquid form, you have a different microstructure. Slowly when it is reaching to this solid liquidous line, so during this liquid point, we have equal compositions. That means the copper and nickel are in the liquid state. So they are equally distributed in that, and we can see the microstructure. Now slowly when the temperature is being reduced, what happens? The system get solidified. So during this solidification process, what happens? How much composition of nickel and the copper is there? Okay, depending upon that composition, slowly there is a solidification start. So this is the solidus line. From this point, the liquid nature will eliminate and the solidification will start. So from this point, slowly if you still reduce the temperature, what is happening here? At this junction, at the point B, you have both liquid and solid particles. Okay, so for this again you have different microstructure. If you see here, it is a combination of some liquid and some solid particles. These solid particles are nothing but the nucleates. Okay, nucleates of nickel and copper. And slowly if you still reduce the temperature, that means you're trying to cool and you're trying to get solidification of that material. So if you're still reducing the temperature, what is happening? It is coming under the alpha region. So what is the alpha region? Alpha region is called the solidification region, complete solidification region. So if you again see the microstructure, you can find out like this, the alpha particles. So this is one of the another microstructure you can see. Like that, there is a development in the microstructure of an isomorphous alloys at equilibrium condition. That means slowly the temperature is getting reduced. You can see here, as we are coming down, as we are decreasing the temperature, what is happening? The material, whatever the material will have, the composition of nickel and copper, it is in the liquid state. So after that, if you reduce the temperature, what is happening? Slowly the material is getting solidified. So at different stages, you are having different type of microstructures. And these microstructures, why we are trying to get these microstructures? Based upon the microstructures, you can infer the characteristics or the properties of the material. So different microstructures will have its own physical and mechanical characteristics, as well as the melting temperatures, as well as the compositions. So compositions also varies here. So in this liquid phase, you have different composition. And coming to slowly at point B, what is happening here? There is a combination of liquid as well as the solid. And here also, if you compare the properties of this, and both these will have different properties when you compare with the physical as well as the mechanical properties. So here again you have another different types of properties. Though it is the same composition, but because of the temperature variation as well as the composition variation, there is a change in the microstructure. So there is a development in the microstructure. So initially it is in the liquid. Slowly, if you reduce the temperature, it is a combination of liquid as well as solid. And if you still further reduce the temperature, it is coming into a solid form. Okay. So you have three types of different microstructures based upon the temperatures. If you want to find out what is the microstructure at this point, again you'll have different microstructures. So at each and every stage of its temperature, the alloys, what are the alloys we are taking, whether it is a copper or nickel combination, it has its own microstructure. So based upon the microstructure, you can justify or you can characterize that material based upon those properties. Now, if you see in this figure, the region of the copper and nickel phase diagram is the density of the composition of the figure. So it is based upon the correct compositions. So if you identify what is the composition of that material at that some particular temperature, it is very easy for us to identify what is the phase diagram. Now, how to identify that composition we have discussed in the previous sessions. So based upon the tie line. So this tie line, when we have to use, if it is in a single phase, that means if it is in a liquid phase or a solid phase, it is very easy for us by stretching the lines along the horizontal and vertical axis, and you can easily get the temperature and corresponding compositions. Now, if the same point is lying in between the two phases, that means if the point is lying in between that solid and liquid phase, what we have to do? We have to use the tie line process. What is this tie line? This tie line has to be tied in between the two phases so that it has to intersect the two phases. What are the two phases here? One is the liquidous line and that is the solidus line. So this tie line has to intersect those two phases, and from that intersection points, what we are trying to do, from that intersection points, we are dropping the perpendiculars along the horizontal line where we are getting the compositions, different compositions at different temperatures. Now if you see here, cooling of an alloy of this composition corresponds to the moving down vertical. So if you go down, if you see this dotted line, what are the dotted line you have here? This dotted line refers to decrease in temperature. So when you are trying to go down, so there is a cooling process is going on parallelly. So as we have discussed, these are the points, the edge extreme points are the melting temperatures. So above that we have the complete liquid state. So below that we have solid state. In between we have the solid plus liquid. Now when you're coming down after melting point, if you stop the temperature, what is happening? That there is a reduction in the temperature. Slowly the temperature is coming down like this. It is falling down. So during the fall down of the temperature or reduction in the temperature, whatever the melted material is there, it is slowly converting into a solid form. Okay, so during this formation of a solid form, there are a lot of changes in the microstructure. And these microstructure variation depends upon the compositions. So now you can see here, different compositions are there here. Different compositions depends upon the microstructure. Whatever the circles you are seeing here, there are the compositions of the nickel and copper based upon the compositions, and with respect to these tie lines, we are trying to extract the compositions and we are trying to find out what is the microstructure of this material during the cooling process. So now here, the first point A refers to liquid state, is it not? Since it is lying above the solidus line, so here the complete area, the complete zone is in the L state, that is the liquid state. Below this is the alpha state or the alpha phase, that is the solidus. Now in between these two red lines, we have the both combination of solid and liquid. Now since the point A is lying in the liquid state, so liquid state, so what is the infer we can get? Directly we can drop the perpendiculars along the x direction as well as the y direction to get what is the composition and what is the temperature. Now at this point A, if I draw a line along the y-axis, I can get the temperature, that is 1300 degrees centigrade is the temperature of that point A. Similarly, if I drop a perpendicular along the x-axis, I can get 35% of composition. So since it is lying in a single phase, so there is no problem. So there is no use of a tie line method here. But coming to the point B, if you see the point B, this point B is lying in between these two phases. So when a point is lying in between two phases, then we have to use a tie line process. So in this A point, we are not using any tie line because it is in a single phase. Since the point B is in double phase, we are using the tie line. And how to draw this tie line? You have to stretch this tie line in such a way that it has to contact the two intersections. So two phases, the point B has to get in contact. That is, it has to tie the two phases. That's why it is called as a tie line. So at this point, we are getting one. At this point, another one. So what is the procedure we have followed in order to get the compositions in a tie line process? Once you draw this tie line, and which this tie line is intersecting two points of the two phases, from those we are trying to drop the perpendicular lines like this, and we are getting the composition. So at this point you have 45% and here you have 35%. Like that, you are trying to get the compositions. If it is 35% of copper, nickel should be 65. Okay, if 35% of copper is there, weight percent, nickel should be 65% of weight at this point. Now similarly at this point, if copper is 45% of weight, then the nickel should be 65. So like that, you have to find out the compositions. So at each and every point, of A, B, C, D and E, you have total 5 points. At each 5 point, you have different compositions, and you have different microstructures based upon whether it is in the liquidus phase or solidus phase or combination of these two phases. Now, if you consider at 1300 degrees centigrade, the point A, whatever the point A we have at 1300 degrees centigrade, the alloy is completely in the liquid nature. Since it is lying, the point A is lying in the liquidus region, that's why at 1300 degrees centigrade, whatever the point A we have, it is completely in the form of a liquid. So how much composition we have? 35 weight percentage of nickel with 65 weight percentage of copper. Exactly, since we are dropping the dotted line, what you are seeing here you are getting 35%. So this is the 35% weight of nickel, and the remaining will be 65% weight of copper. So this is the complete combination of liquid. It is in the complete form of a liquid at point A. So that we are representing here. That's why it is in L. That is a liquid, 35% of nickel. So the remaining will be 65% of copper. Now if it slowly comes, what is happening as cooling begins? So as cooling, when the cooling starts, when you reduce the temperature, when you stop the temperature, slowly the cooling process starts. So as cooling becomes, no microstructure or compositional changes will be realized until at what point? until you reach that solidus line. So where is the solidus line? Approximately it is at 1260 degrees centigrade. So up to 1260 degrees centigrade, there is no change in the microstructure. Why there is no change? Since it is under liquid nature only. Since it is under liquid phase, there is no change in the microstructure. But once it reaches to 1260 degrees centigrade, that means this red line, the point B, then there is starting of a solid. So there will be some combination of the solid as well as liquid. So before 1260 degrees centigrade, from 1300 to 1260, there is no change in the microstructure since it is in the form of a liquid phase. Now if you see, at this point, you have 35% of nickel and 65% of copper at this point. Now, slowly if you reduce the temperature at point B, what is happening? At point B, again you are drawing a tie line here, which is connecting the two intersection of the faces. After connecting, you drop a perpendicular along this point, Now, how many compositions you are getting? We are getting 2 compositions. So, this is the solid nature. That's why we are writing it as alpha. What is the alpha here? Alpha is the solidus line. This is the solidus line, is it not? So, this is the solidus line. So, what is the value, the composition of nickel? If you drop here, so around at this point, you are getting 46% of weight percentage of nickel. That's why we are writing here alpha 46 nickel. So at this point. Now similarly, if you stretch along this point, again if you drop a perpendicular, you are getting here how much? 35% of nickel. 35% of nickel. So if you see the microstructure of this point, so liquid will be 35% of nickel, and what is the remaining? Remaining will be alpha as 46. The solid material, whatever the solid material you're seeing here, this we are representing here. So these are the solids. Solid formation is starting at the 1260 degrees centigrade. At this point, if you compare these two microstructures, so here you have complete liquid nature. But if you see here, you have some solids are also forming. The nucleates are also forming of alpha particles. That is the solid particles. So what are the solid particles are there? How much? 46% of nickel. So this we are showing here. So this is how you have to find out the composition at that point B. Now slowly if you still reduce the temperature. So if you reduce the temperature, so what is the next point we can see here? C. Point C you have. So this point C is also lying in between these two faces. So again a tie line has to be drawn. So another tie line, the blue color whatever you are seeing here, this is another tie line which is passing from the point C and also intersecting the two faces. So at this point you have one intersection, at this point you have another intersection. So again what we have to do, you have to drop the perpendiculars from these two. So one, so another. So if you see the percentage, somewhere 32% you are getting here, and here if you see you are getting 43%. So like that, there is changes in the compositions. Since there is change in the composition, the microstructure is also getting changed. Now this point C is represented here in this figure. So this is the microstructure. Now this point refers to the solid particles, that alpha region. That's why there is an increase in the size of alpha here. So what is that alpha you have? 43% of nickel. So now if you compare the point B with C, you can clearly observe there is a difference in the nucleates, difference in the solid particles. That is, there is an increase in the size of the solidity. That means you are cooling the temperature. So what is happening? The liquid form is converting slowly into a solid form. It won't drastically suddenly form into solid. Slowly, since it is an equilibrium condition, what is happening? Slowly the temperature is getting reduced and that liquid form is being converting into solid form based upon the compositions as well as the temperature. Since you have more percentage of nickel in this, nickel is getting solidified quickly when you compare with the copper. Why? Because you have the high melting point of copper when you compare with the nickel. That's why nickel is getting solidified more quickly when you compare with the copper. So here whatever the solid particles you are seeing, it is of nickel. Maximum nickel composition is there. So these are the 43% of nickel. And what is the remaining percentage here? Here you have 32. At this point you have 32% of copper. So this you are representing here. So this is how you have to show what is the composition at point C. Now if you still reduce the temperature, what is the other point? We have the point D. So this point D, so this also is lying in between the two phases. So again a tie line has to be drawn. Total at these points B, C, D, totally we have drawn 3 tie lines, and based upon these 3 tie lines we are trying to extract the compositions. Now at this point D, again this from point D you have to draw a tie line between the two phases. Again you get one junction here, another junction here. So slowly drop a perpendicular at this point, and of course along this point. So here you are getting 35%, and here you are getting some 24%. So the same thing you are writing here, 24% of nickel, and what is the value here? 35%. So the point D phase diagram or the compositions can be shown like this. 35% of nickel, which is alpha in nature, that is solid nature. So wherever you see that alpha and L, alpha refers to solidity, solid nature, and L refers to liquid. That means 35% of nickel is being in a solid form, and 24% of nickel is in the liquid form. So that is the different phases what you have at different temperatures. So that is how you are representing here. When you still decrease the temperature, if you further decrease the temperature, what is happening? You are getting the reduction in the temperature at some point here, the point E. Still reducing, still cooling the temperature. So at this region you have again a single phase, the complete solid phase. Why? Because you are coming out of that two phases here. So that's why there is no use of tie line at point E. If the point E is also lying in between, then you have to again draw the tie line process. But since the point E is completely coming down and it is in the single phase only, that is in the solid phase, so directly we can take the compositions by dropping the horizontal and vertical lines along the x-axis and y-axis. So at this point from point E, I am dropping a perpendicular line and a horizontal line along this point. So here you are getting some temperature around below 1200 degrees centigrade, and this point you are getting 35% of nickel. So since it is in the solid, that's why if you see this microstructure, it is in the complete form of a solid, full form of solid. See, there is no gaps here when you compare with the microstructure of the previous temperatures or the previous compositions. There is some portion of liquid. Why? Because it is coming under the two phases. But here, since it is the point E is coming completely out of that phase, and it is in the form of a solid phase, that's why the microstructure of this point E is in the complete form of a solid, and the composition is 35%. So this is how you have to draw the cooling curves of the given composition with respect to the single phase or double phase. Now from these figures, it is very easy. If you compare the point A, so the point A is completely in the liquid form, that's why you are writing L, that is in the liquid nature. So single phase, that's why it is L, 35% of nickel. Slowly, if you reduce the temperatures, it is touching the point between the two phases. That's why you are drawing a tie line. So if you compare the phase diagram or the microstructure, you can see there is a lot of difference. There are some solid particles are being formed. So by drawing the tie line, and from those tie lines, if you draw the perpendiculars, you will get the total composition. So this is another microstructure at point B. At point C, the point C is also lying along the two phases. That's why there is an increase in the solid nature. So the size of the solid particles are increasing at point C by reducing the temperature. If you still reduce the temperature at point D, then there is an increase again. There is an increase in the solid particles. So that's why you can see the increasing. But there is some gap there. So this gap represents for that other phase. What is the other phase? You have liquid nature. That's why liquid percent is getting reduced and solid percent is getting increasing. So that means this refers to the reduction in the temperature. Because of the reduction in the temperature, the liquid nature is getting absorbed and the solid is being forming. That's why the solid percentage is very, very high when you compare with the liquid nature. And if you still reduce the temperature, there is a no formation of liquid, there is a complete formation of solid particles here. So this is how the schematic presentation of the development of microstructure. So this is how there is a development. So changes how it is being developing from liquid nature to solid nature of this isomorphous alloys. And this point is specifically at the composition of 35 weight percentage of nickel and 65 weight percentage of copper. So this what are the example we have taken. So in any cases, if they are asking any other type of composition, then you have to shift that point. This dotted line has to be shifted. So since it is 35%, we are getting exactly at 35%, we are drawing this dotted line. If the composition changes to 40 or 45, then you have to move this dotted line to here. And you can see again how it is being varying the development in the microstructure. Now, at this point, the first solid alpha begins to form, is it not? At the point, exactly at the point where the alpha nature, that is the solid phase is there, it is being formed, and the composition can be identified with the help of drawing the horizontal lines along the x-axis and y-axis to get the compositions. And based upon those horizontal and vertical lines, you have to calculate how much amount of nickel as well as the copper present in that temperature. So now by cooling process, the points are changing from A, B, C and D to E. So depending upon those points, and if those points are lying in the single phase, then it is very easy for us to find out the composition. And if those points are lying in between the two phases, then you have to use this tie line process and you have to identify different compositions, and based upon those compositions, you have to draw the microstructure of that alloy. Now, further, if you want to have the total percentages, so the percentages calculations we have discussed in the previous classes, so you have to identify the distance, the total length of the tie line. From that length of the tie line, you have to identify which area is about the liquid and which area is having the solid zone. And from those zones, you have to take the fractions, and if you multiply with the 100, then you will get the total percentage of composition present at that point and with the respective temperature. Now, overall composition of the alloy, what we have taken here is 35% of nickel and 65% of copper. So this is remaining unchanged until at what point? Until that liquid nature. Okay, so until the liquid nature, this composition will remain unchanged. But when it starts cooling, when the cooling nature starts, so what is happening? There is the reduction in the temperature. So because of this reduction in the temperature, there are changes in the composition. So this composition will change now. It won't remain same. Because of the cooling nature, what are the composition we have taken 35% and 65%, these compositions will vary. And to identify those compositions, we are using that phase diagram. With the help of that phase diagram, we are trying to identify at corresponding temperatures what is the composition. Now at 1250 degrees centigrade, the change of the composition will start. Why the change is the composition? Because the liquid nature is slowly evaporating and the solid line is entering. So because of the solid line is entering at 1250 degrees centigrade, the composition, whatever the composition we have as 35 and 65, this is being replacing with 32 and 68. Slowly like that it will change because the liquid nature is being evaporating and the solid nature is being starting. So this is how there is change with respect to the temperature, and the temperature has to be reduced. So reduction in temperature indicates that the particle or the material is being cooled and it is trying to get into solidified nature. So since the solidification starts virtually at 1220 degrees centigrade, so at this point this line is being started. What are the line you are seeing here? Exactly it is at 1220 degrees centigrade. That means the liquid nature is slowly converting into solid. So that's why the composition, what are the composition we have 35, 65 is slowly converting, changing into other compositions like 724, 76 like that. Again, wherever you see the balance, there should be some balance. If you add these two weights, it should be 100. Since you have only two compositions here, the combination of these two should be 100%. That's why wherever you identify, exactly you'll get the 24 plus 76 again 100, 35, 65, 100, Okay, the composition should be equally, it should be 100 wherever the point it is. But at this point, the solidification starts. That's why there are changes, total changes in the microstructure at different points. And if it is completely coming in the solid nature, if you see this point, if you compare the point A with point E, if you compare point A and point E, if you see this microstructure for these 2 points, point A is having complete liquid. Why? Because it is in liquid phase. And the point E, if you see, we have complete solid because it is in the solid phase. Now, if you see other points as B, C and D, B, C and D, these are all combinations. Why? Because these B, C, D points are lying in between the 2 phases. That's why you're getting the combinations of solid as well as liquid. So upon crossing the solidus line, that means if you cross this solidus line, what is happening? The solid nature increases. Solid nature increases. That means there is a change in the microstructure. So like that, you have different developments in the microstructure based upon the temperature. And the subsequent cooling will produce no microstructure composition alteration. So once you change the phase, then only there is some change in the microstructure. If it is in the liquid, you'll have the same nature of microstructure. If it is the solid thing, it will be having a solid nature of microstructure. But if it is in between, then there is a change in the microstructure that you have to identify. So that is about equilibrium, where the cooling temperature is being slowly converting. Okay, but coming to non-equilibrium cooling, there is a rapid, fast cooling of the material. So during this, there is a lot of change of the microstructures because it is a rapid cooling. When we compare with the equilibrium, there is a slow process of cooling. That's why you have a good nature of microstructure when you compare with the non-equilibrium type of bodies. So these non-equilibrium, since they are having the fast or rapid cooling nature, you have different microstructures. When you compare the same metal, if you take the same copper and nickel, so these 2 materials, when heated to melting points, after melting points, these 2 are said to be cooled. One is at equilibrium, another is at non-equilibrium. And if you see these, when you compare these 2 microstructures, so one is getting rapid cooling, another is getting slow cooling, that is non-equilibrium and equilibrium. So you can identify a lot of changes in the microstructure. So the previous session, whatever the thing we have discussed, it is about equilibrium. Now this is about the non-equilibrium. Since you have the rapid development in the cooling, how to draw or how to represent the microstructures we'll see based upon the phase diagram and considering that liquid nature of the particle. So the same thing we can take as 35% weight of nickel and 65 weight percentage of copper of the same composition. And if you go under the non-equilibrium condition of cooling, then what are the things we can see here one by one. Now, if you compare this figure exactly with the previous equilibrium condition, there are a lot of changes in the microstructure. Of course, the point A, since this point A is in the liquid nature, there is no changes. So you have a liquid microstructure here, combination of 35% of nickel and 65% of copper. There is no alteration. But once, if you reduce the temperature, this A dash, what are the A dash you are seeing? This A dash represents for non-equilibrium condition. If the figure is having only A, then it represents for equilibrium. So since it is a dash, A dash, that means this is representing non-equilibrium cooling. That means rapid cooling of that system. Now, if you reduce the temperature, so it is coming to point B dash. This is the B dash with rapid cooling. Now, if you, this B dash, again, it is falling under the 2 phases. So what you have to do, you have to again draw the triline. So from the triline, you have to find out the intersections of the 2 phases. Again, from the intersections, you have to drop the perpendiculars to find out the composition. So since the point B is lying between the 2 phases, I am drawing a triline here, which is having the 2 intersections here. And the compositions, if you drop along the horizontal line, you are getting 46% of nickel and the remaining will be 35% of liquid nickel. So that you have to represent here. So 46% of nickel, which is in the solid form, since this is the solidus line. So 46% of nickel is at this point and the remaining liquid is 35% here. So that you are representing at this point. Now if you slowly reduce the temperature, you are getting the point C, and this point C is also lying in between the two faces. You have to draw this line, the tie line, and again try to get the compositions. So you have to represent here. Now if you see this point C, you can note there is a dark line and a thin line. That means the dark represents for, since because it is a rapid cooling, okay, the solid formation is happening very quickly at this point, but towards the surroundings you are not getting that much complete solidification. Since it is a rapid, it is taking some time to get cooling or to become solid form. That's why see here 46% of nickel of solid nature and 40% of again nickel, it is solid, but it is not that much solid. That's why there is some change in the color, and the remaining is 29% of nickel, which is in the form of a liquid thing. Next, coming to the point D dash, again since the D dash is lying between the two faces, again you have to draw the tie line, and from the tie line you have to find out what are the compositions here, and again if you draw the microstructure for this, so you can see here, you can identify you have dark dot in between, and again another change in color. So three different variations is there. Again, because of the rapid cooling in the system, there is a changes in the solidification timings. Okay, at this point you have good solidification. Slowly if you come out, you have less solidification. If you further come out, so 3 layers it is forming of solid nature. So here the solid nature of 46 of nickel, 40% of nickel, 35% of nickel, and the remaining will be a liquid form of nickel. So this is how you can identify the microstructure. Now if you still come down the point E, now you can see this dotted line. What are the dotted line you have? So you have to draw a parallel line from the junction of point B. So since it is passing between the two faces, so you have to draw another line here from this point E and identify what is the compositions by dropping horizontal and vertical compositions. So you can see here, this is another different microstructure of that nickel and copper compositions, which is having different compositions of solidity nature, and 3 different types again you have, and another thing is you already have a liquid. So total 1, 2, 3, 4 and 5. So 5th one is a liquid, and other 4 will be in the form of a solid. And these also, the solid, it is not a single solid, you have a multiple solid of layers. So each layer is having different temperatures. Okay, that you have to identify. And if you come down still, if you reduce the temperature, it is under solid zone. It is completely solid zone. That's why it's a single phase. Directly you can drop the perpendiculars along x and y directions. You can identify what is the temperature at this point and what is the composition at this point. From this, you can show the compositions along the x and y axis with respect to the temperature. So this is how there is a lot of difference between the equilibrium and non-equilibrium conditions, where there is a development in the microstructure of isomorphous alloys. So at each different point, we have different microstructures, whether at point A dash, B dash. So all this A dash, B dash, C dash or D dash, wherever you keep these, it represents for non-equilibrium condition. So in the previous equilibrium conditions, we have only A, B, C, and if you have A dash, B dash, C dash, this refers to the non-equilibrium conditions where there is a rapid type of cooling. So because of this rapid type of cooling, there is a changes in the solidification timings also. You have timing, you have lot of time here to get cooling nature and to form in the solid form. And there is a composition changes also. Up to the liquid nature, there is no change in the composition, but when it touches the solid line, that is the B point, then there is a change in the compositions. So earlier we have taken 35 and 65. Now slowly after coming down, reduction in the temperature, the compositions will also vary. So at this point, about 1240 degrees centigrade, there is a change in the composition. So in the previous cases at 1260 degrees centigrade we have, but in this case at 1240 only, we are getting the changes in the composition. So that is how you have to differentiate between the equilibrium and non-equilibrium compositions in order to develop the microstructure of isomorphous alloys. And In order to get those compositions percentage, we have to draw the tie lines. The tie lines has to be drawn between the two faces only, not in the single face. Based upon those tie lines, we are getting the compositions along the x and y axis. Okay, so this is how you have to draw the phase diagrams based upon the equilibrium and non-equilibrium conditions. And if it is an equilibrium conditions, you have to identify where is the development of the microstructure depending upon the temperature. And since it is a slow process of cooling, you have a good microstructure in the equilibrium condition. And in the non-equilibrium condition, since you have a rapid cooling, then there is a lot of difference between the cooling timings and the microstructure when you compare with the equilibrium conditions. So if you want to have the references for this development of microstructures in the phase diagrams with respect to isomorphous alloys, you can refer these books, Introduction to Physical Metallurgy, and another one is Essential of Material Science and Engineering, and another book is Material Science and Metallurgy. The last one is Material Science and Engineering. So these are some of the references where you can get the information about the interpretation of these phase diagrams, development of phase diagrams with respect to equilibrium and non-equilibrium conditions. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.